Welcome. My name is Peter Deldorf from Atkins Realis. In this video, we will show you how to calibrate SAGIS-SIMCAT models using tools developed for Acquia. The purpose of calibration is to better align the model with monitoring data from the real world, such as river flow monitoring data or water quality monitoring data. The process of calibration makes adjustments to the inputs of diffuse flow to each reach in the model and adjustments to chemical loads. The calibration adjustments to a SAGIS-SIMCAT model are applied via tables in the model databases. These are created outside SAGIS-SIMCAT, which I will show you later in this video. Here we can see an example of one of these adjustment tables. Each row in this table represents a model reach, as you can see on the map. There are two fields of note, reach adjust and reach adjust Q95, and the values in these fields apply an adjustment to the diffuse inflows for each reach. We are now looking at a water quality calibration table. This is similar to a flow calibration table in that each row represents a reach in the model. In this case, for a particular determinant as specified under DEC code, this is nitrate. In this case, though, the adjustments are made to the diffuse inputs. For example, LS-AG represents adjustments to the livestock inputs, and AR-AG represents changes to the arable inputs. As you can see, there are further sectors going across, adjustments to other sectors, and then further across are adjustments that change the variability of the inputs. SAGIS applies the adjustments in these calibration tables when it creates the SIMCAT DAT file, as you have seen in previous videos. To do this, if you recall, you go into SAGIS and then SIMCAT, and then into Create SIMCAT file. Part of this form, there is a section on calibration. To apply flow calibration, simply click on this box. Below are listed in the drop-down box all the calibration tables for flow that have been created previously. Note that all tables must start with the words flow calibration table. This is how the model recognizes them as calibration tables. For water quality, exactly the same. Click on the box and then again, pick the one we wish from the drop-down box. To continue the Create SIMCAT process, click on Run as you have seen previously. We are now going to look at the external tools developed for Acquia to calibrate SAGIS-SIMCAT models. These create the calibration tables that you have seen previously. There is one for flow and one for water quality. We are now looking at the one for flow. These can be obtained from the Environment Agency along with the SAGIS databases. I'm now going to show you some of the key information that you need to enter onto the Controls tab. When the calibration tool runs, it creates a new SIMCAT DAT file. This has the same name as the pre-existing DAT file with an extension, which is defined in this box B4. For example, if the pre-existing DAT file was called test.dat, the new one produced by the calibration tool would be test-flow-cal.dat in this example. The next key bit of information is located in cell B14. This is the location of the SIMCAT executable on your computer or system. The following cell down is the location and name of the pre-existing DAT file that you wish to calibrate. This needs to be run before the calibration tool is used. Finally, in cell B18, this is the name of the new calibration table that the tool will create. If you recall, this table has to start with the name Flow Calibration Table, after which you can put further characters. In this example, we have added the date, which is good practice because it tells you when the table was created, but other characters can be used as you wish. As you can see, this tool is an Excel workbook, and we're now looking at the Controls tab, where most of the inputs are entered to set up the tool. There are many other tabs that do calculations and present the outputs. I'm now going to show you some of the other settings on the Controls tab. Often these do not need to be changed. The first one I'm going to show you is in the Adjustment Limits section in B23 and 24. This specifies the magnitude of change that is permitted within the calibration process. So in this case, the maximum adjustment is 4 and the minimum adjustment is 0.25. As a result, the diffuse inflows can be increased up to a factor of 4 and decreased likewise by a factor of 4. In the cells below, in B25 and 26, this specifies the maximum flow per kilometer and the minimum flow per kilometer that is allowed within the SIMCAT DAT file as a result of the calibration process. This prevents unrealistically high or low flows being created in the DAT file as a result of the calibration process. Similar limits are placed on the Q95 in the cells below, in B27 and B28. Once these entries have been made onto the Controls tab, we can run the calibration tool. This is done by clicking on the arrows, starting at the one at the top and then working your way down the sheet. I will go through these in turn. As you can see, the first arrow is called Setup. When we click on this, this reads information from the SIMCAT DAT file and transfers it to the sheets within the calibration tool. I'm going to click on it now. When you do, this box will appear. I'm going to click Yes. I'll explain why shortly. You see, very quickly, information was read from the SIMCAT DAT file. If we go down the sheet, we can see in this determinand section, the chemicals within the DAT file have been added. Before proceeding, we need to add further information. In column D, we need to add a default concentration for effluent water quality for each of the chemicals within the DAT file. And in column E, the COV, and in column F, the correlation coefficient. This is a correlation between effluent quality and effluent flow. We also need to add values for effluent flow for the COV and for the correlation. In this case, it's the correlation between effluent flow and river flow. If you recall, when we clicked on the green arrow, a box came up asking you whether you wish to replace the values in the determinant section. If you are starting on a new calibration with a new DAT file, it's quite likely that determinants will be different to when the tool was last used. In this case, you will want to replace the values. I've now added some values, as you can see, as examples. However, if it is not a new DAT file and the determinants have not changed, you can click No and retain the pre-existing values. This might happen, for example, if you want to repeat the calibration after adjusting some of the settings. We can now go on to the next stage in the calibration process. As mentioned before, this involves clicking on the arrows starting at the top and going down the screen. The next arrow is the Create and Run SIMCAT Files arrow. When this is clicked, the tool creates a series of new SIMCAT DAT files and runs SIMCAT. It then takes the outputs from these model runs and extracts information from them to feed into the tool, and these are used to calculate the adjustments. So now we can click on the arrow. As you can see, SIMCAT starts running. We need to wait for these runs to complete before clicking on the next arrow. 3 SIMCAT models are run. Once these runs are complete, we can move on to the next stage of the calibration. As before, we click on an arrow, in this case the third one down, called Review Flow Gauge Selection. When we click on this, it reads in the outputs from the SIMCAT model runs that have just been carried out. Information from these outputs is entered into the sheets of the calibration tool. Before looking at the outputs, I'd like you to first look at the values in cells B31 and B32. These specify a deviation between the model outputs for river flow and the observed data at flow gauges that is considered acceptable. The reason for doing this is that some flow gauges are known to be unreliable, particularly for certain parts of the flow duration curve. These thresholds help you filter these out. Outputs from the SIMCAT model runs are processed and summarized on another tab called Intermediate Outputs. As you can see, information is included on the observed Q-mean and Q95 and the simulated mean and Q95 for the 3 model runs. These are compared alongside the threshold that I just mentioned, and if the deviation is too much, these are flagged by a 1 in column C. A 1 indicates that they are outside the specified range. A 0 means they are fine. In this case, all 4 gauges are fine. If a gauge is identified as outside the specified range by a 1 in column C, it will not be included in the subsequent calibration. However, if the user wishes to include this gauge, because, for example, there's confidence that it is reliable, then the 1 can be manually changed to 0, and then it will be included in the calibration. We can now go on to the next stage in the calibration process, in this case by clicking on the 4th arrow down, Calculate Adjustments. When this arrow is clicked, the outputs from the 3 SIMCAT model runs that have already been processed and entered onto the sheets are used to calculate the adjustments required to achieve an optimal fit with the observed data. I will now click on the arrow. As you can see, almost instantaneously, it calculates the adjustments that will subsequently be applied to the SIMCAT model via the flow calibration table. The next step is to click on the 5th arrow down, Create SIMCAT and Run. This applies the adjustments to a new SIMCAT DAT file. If you remember before, it was given the extension flowcal in this example, and it runs this new SIMCAT DAT file. I will now click on the arrow. If you wish to run, say yes. And as you see, SIMCAT starts to run. This is the new DAT file with the adjustments. As before, you will need to let it run to the end before going on to the next stage. The next step is to click on the 6th arrow, Process Outputs. This reads in the model outputs from the SIMCAT run that has just been carried out, but also makes a comparison with the original DAT file outputs. As you can see, this runs very quickly. After this, click on the View Performance arrow. This takes you to another sheet called Performance. On this, you can see a comparison between the model performance before and after calibration. On these charts, the grey dots and grey bars are before calibration, and the black dots and black bars are after calibration. Sometimes you need to click on the Change button to update these charts. As you can see in the scatter plot, we're trying to achieve a one-to-one relationship between the simulated and observed. The grey dots are before calibration, that shows they are quite substantially below the observed data, whereas after the calibration, we have a much better fit. For the Q-mean, the original model performance was much better, but still we're seeing an improvement with the calibrated model. These outputs are shown in a different way in the bar charts. Here, the x-axis is the ratio between the simulated value and the observed value. And on the y-axis are the number of gauges falling into each category. So what we want is all of the gauges to be around 1, which is a one-to-one relationship between the observed data and the model outputs. For the Q95 in particular, we see before calibration, a lot of the gauges are well below the observed value, which is the grey bar. Afterwards, the black bar, they are much closer to the one-to-one ratio. After calibration is complete, the outputs are summarized in a sheet called Final Calibration Table. This is the calibration table that is sent to SAGIS-SIMCAT, as you saw at the start of the video. Again, if you recall, in field Reach ADGE is an adjustment of the Q-mean, and in Reach ADGE Q95 is an adjustment for the Q95 for each model Reach, which is each row of the table. Before the final stage, you can make adjustments to these values if you feel you want to achieve a better fit for a particular part of the model. The final step is for the calibration tool to issue the final calibration table in a form that can be read in by SAGIS-SIMCAT. Simply click on the final arrow, Create Flow Calibration Table. This creates a new Excel spreadsheet containing the final flow calibration table. If you recall, when we set up the Control tab, we provided a name for the new calibration table in cell B18. This name is given to the new Excel spreadsheet containing the flow calibration table, in this case, flow calibration table _06032025.xls. This file is sent to the same folder as the original DAT file. It is this file that is read in by SAGIS. Before leaving the flow calibration spreadsheet, I would like to also point out that there is a README sheet, and this provides more information on the calibration process and how to adjust some of the settings. We are now going to look at the water quality calibration tool, again an Excel workbook. It has many similarities with the flow calibration tool, but the principles in which it operates are different. Whereas the flow calibration tool calculates the adjustments directly, the water quality calibration tool makes calculations, but these are then tested by running SIMCAT again, and then further adjustments are made in an iterative fashion. I will now show you how to set up the water quality calibration tool. As before, this is done on the Controls tab. In a similar way to the flow calibration tool, we need to enter in the Data Sources section the location of the SIMCAT.exe file, the location and name of the SIMCAT.dat file, and the name of the new calibration table that the tool will create. Usually, we will create a version of the SIMCAT DAT file to which the flow calibration adjustments have been applied and use this for the water quality calibration. This will mean that the flow calibration adjustments are taken into account before we carry out the water quality calibration. I will now show you some of the other key settings on the Controls tab that you need to consider when setting up the calibration. Firstly, we need to consider what type of calibration we undertake. In the drop-down box in cell B3, we will see there are a number of options for how the calibration takes place. If we select mean only, this will mean that only the mean chemical diffuse loads will be changed. Whereas if we select mean and COV, this will mean that the COV is also adjusted, which will change the variability of the loads. This is particularly important in relation to percentile values in the simulation, and especially important, therefore, for chemicals with percentile standards. Another option is to include adjustments to decay rates in the calibration process. In this case, by selecting mean COV and decay, or decay only. Adjustments to mean and COV cannot take place at the same time within the tool as adjustments to decay. If all three are selected, we must specify which iteration applies mean and COV adjustments and which iteration applies decay adjustments. This is done in another part of the spreadsheet toward the bottom in the sequence section. In this case, for each iteration, we specify whether to apply decay, either yes or no. Normally, we would start with no, so no decay calibration, and then have perhaps one or two of the iterations where there is decay, so we put in yes. It's also important that the last iteration should be no. The number of iterations included in the calibration is specified in cell B4. Because water quality calibration could take several hours on a large model, there is a compromise between the number of iterations and therefore the improvement achieved and the length of time this takes to complete. Up to 10 iterations are possible, but normally we'd carry out 4, 5, 6, for example. Another important section of the Control tab is the Adjustment Controls section. In this, the maximum and minimum degree of adjustment is specified for the diffuse input, the COV, and the decay. For example, in this case, the maximum adjustment for the diffuse loads is 50 and the minimum is 0.1, so it can be reduced by a factor of 10. The range of these adjustments that are applied is largely dependent on the degree of confidence you have in the input data. If you have a high degree of confidence, you may not want to have much adjustment, whereas if you have no idea if the inputs are right or wrong, you may want to allow a large adjustment. Another important section on the Control tab is the Monitoring Point Selection section. In cell B40, the percentage that point sources make of the concentration at a monitoring point is specified, above which the monitoring point is not included in the calibration. The reason for this is that the information on diffuse concentrations is likely to be less reliable at these locations. Likewise, a threshold for the decay calibration can be set in cell B41. Also note that some of these settings can be set on a chemical by chemical basis in the determinants section. Once you're happy with these settings, you can now move on to the calibration itself. There is an option to run down the arrows in the same way as the flow calibration, but this only completes one iteration. The preferred approach is for the tool to carry out all the iterations in an automated way. This is started by clicking on the orange arrow, Run in Iterative Calibration. If you now click on the orange arrow, this box appears. When you're running the automated calibration, just click Yes. Another box appears, click OK. As you can now see, SIMCAT starts to run. In each iteration, 8 runs of SIMCAT are carried out in total. So if you select several iterations, this is clearly a large number of runs, which will take a long time, many hours for a large model. Once the model runs have completed, we can look at the performance of the calibration on the iterative performance sheet. The graphs on the right show how the performance changes with each iteration compared to the pre-calibration values. The upper chart shows 2 types of t-test result for each iteration. The lower chart shows the percentage of monitoring locations in which the observed data and model output are within 25% of each other. The graphs in the middle show scatter plots between the model output and the observed data before and after calibration for both the mean and the 90th percentile for an iteration specified in the drop-down box on cell E3. In this case, iteration 8. The charts on the right-hand side show histograms of the ratio between the model output and the observed data. As with the flow calibration tool, we are looking for a ratio of 1, and we can see here the improvement between the pre-calibration in grey and the post-calibration in black. To change the iteration that we are looking at, simply go to the drop-down box, pick a different iteration, and select Go. And we'll shortly see the results change. Likewise, we can change the chemical by selecting a different one. In the first drop-down box, we'll pick ammonia, and then click Go. And again, we see the values change. If after looking at all these iterations, you think there is one that is better than the final iteration, you can apply the adjustments for this iteration to the final calibration table by selecting the chemical and iteration and then clicking on this Apply to Final Calibration button. As before, with the flow calibration tool, the final calibration table can be seen on the Final WQ Calibration Table tab. Manual adjustments can be made to the values in this table before it is issued to SAGIS-SIMCAT. This is done by going back to the Control tab and clicking on the red arrow. This creates a flow calibration spreadsheet in the same folder as the original DAT file. Also note there is a README tab in the water quality calibration tool. This provides more information on the calibration process and some of the settings. We have now created our calibration tables. The last thing I will show you is how to import these into SAGIS. All we have to do is go into SIMCAT and then import calibration data. This brings up a geoprocessing tool. In the first box, we select one of the calibration spreadsheets that we have created. In the second box, we navigate to the regional database and enter the name of the new calibration table. In this case, we're adding a flow calibration table. An easy way to do this is to go to a pre-existing calibration table and add some extra characters. You see this is now in the box. You have to select Export in this box and then click on Run. This will enter the calibration table into SAGIS. If now we go back to the Create SIMCAT file form, we can see in the drop-down box listing the flow calibration tables, the one we have just added. This can now be chosen and used to create a new DAT file. This concludes the video. You are now ready to calibrate your own SIMCAT models.